Hello everyone. Today we want to talk about the nozzles and diffusers. We already talked about the first law of thermodynamic and conservation of mass applied to open systems. So we want to talk about a specific system, which is basically nozzles and diffusers. So a nozzle, what is a nozzle? A nozzle is a device that increases the velocity of a fluid, right? So if you look at the picture on the left, you can see that the fluid can enter from the left side with a velocity v1 and then it can exit from the other side with much higher velocity. So there is a velocity change happening here, and this velocity change should be such that basically that the exit velocity is much higher than the inlet velocity, and that is called a nozzle. On the other hand, we have diffuser in which basically the velocity drops. So the fluid enters from the left side and then exit from the right side of this device with much lower velocity. Okay, so we want to write basically the first law of thermodynamics for this open system, and we consider this dashed boundary, which is our control volume, as our system, and we want to write the first law of thermodynamics for this. So if you remember from previous slides, we have basically this equation on the top that describes the first law of thermodynamics, right? So Q minus W, Q dot, which is basically the rate of heat transfer, and W dot is the rate of work being done on the system, or the system is doing some work. And please notice the sign convention. Heat input is considered to be positive, work output is considered to be positive in this equation. So Q minus W is equal to sigma. This is the total mass transfer. For open system, if you remember, you have basically the enthalpy instead of the internal energy in your equation, and that is due to the fact that we have an extra work, which is the fluid work. U plus PV comes into your equation. This is the fluid energy or fluid work, and U is internal energy. Sum of these two is giving you the enthalpy, and that comes into your equation. This is for open system. For closed system, you had internal energy in your first law of thermodynamics. So you have to write basically this equation for all the exits and all the inputs, inlets, and then try to solve this equation. So we want to do the same thing. So for nozzles, if we consider that there is no change in the elevation of our system, then these terms are going to be zero for nozzles and diffusers. There is a velocity change, and usually in diffusers and nozzles we don't have any heat transfer and no work is being done. So basically the left hand side of the equation is also zero, and what we have left is basically the enthalpy and velocity change. So if you look at the equation on this slide, you can see that energy in is equal to energy out, and then you have to basically write the equation for the entrance, any inlet, and write the equation for exit, put them equal to each other, and that's what you get, right? Now usually one of the velocities are much lower than the other velocity, so you can ignore that velocity too. Okay, we'll do an example on that. So let's see, I think we have an example here. So we have a steam at 250 psi, 700 degree Fahrenheit, steadily enters a nozzle whose inlet area is 0.2 square feet. The mass flow rate of the steam through the nozzle is 10 pounds per second. Steam leaves the nozzle at 200 psi with a velocity of 900 feet per second. Heat losses from the nozzles per unit mass of the steam are estimated to be 1.2. Determine the inlet velocity, the exit temperature of the steam. So this is an example problem of the nozzles, and we are trying to write the first law of thermodynamics as we just discussed for this open system. So where should we start with this? So first, basically, it's steam, right? And we know, you guys know that we have tables of data for these, for the steam, for water, for vapor liquid equilibrium of water. And we start by writing the information that we can get. So what we want to find is basically the velocity at the inlet, right? So we want to find, let me see if this works correctly. Oops. Yeah, okay. So that's what we're gonna do, and let me change the thickness of this so I can write easier here. All right. Yes, okay, it works. And all right, so now what is the initial pressure, inlet pressure? P1 is 250 psi, right? And T1 is equal to 700 degree Fahrenheit. So what do we do? This is basically, we have all the information about the inlet. We can go either to the tables of temperature based table A4 or A5, but we should go to A4E, A4, A5E, because this is English unit. So if we go to that pressure or temperature, either one, and we can find basically the specific volume and enthalpy of basically our system. And table A4, A5 are for liquid vapor mixture properties. However, this is basically steam, so it's at this point it's considered to be a superheated vapor, so we need to go to the superheated table, which is basically table A6E. So from table A6E, we basically can find the information for this specific state of steam. So nu one is 2.6883 cubic feet per pound mass, and H1 is equal to 1371.4 BTU per pound mass. Okay, so now we can find basically the information we need. We want to find the velocity, and we do have also the mass flow rate of our system, right? So m dot is equal to what? Density multiplied by velocity. So we're talking about basically the entrance, right? So that's density at inlet, velocity at the inlet, cross-sectional area at the inlet, and we can write basically density to be equal to 1 over specific volume multiplied by velocity at the inlet multiplied by cross-sectional area. And if we put the numbers in, it's gonna be, velocity is gonna be equal to 134.4 meter per second. So that's basically the part one. Part B, we are required to calculate the exit temperature. So we can use the first law of thermodynamics to find the, because we do have the inlet enthalpy, we can find the outlet enthalpy, and if we have the enthalpy and pressure of the outlet, right, we can find the temperature of our system, right? So what does the first law of thermodynamics look like for this system? So m dot multiplied by enthalpy of the entrance plus velocity square divided by 2 is equal to, please notice that we have a heat loss in this system, right? This is not just the heat is not zero for this specific problem, right? So we have a Q which is going out, and we have plus then m dot H2 plus V2 squared divided by 2, right? So we have H1, right? This number is given or not given. Basically, we found it from the previous part, 1371.4, table A6E. We have the m dot value to be equal to 10 pound per mass, right? 10 pound mass per second. And we have the entrance velocity, and the entrance velocity is equal to 134.4. That's what we found from previous part. So 134.4. We have the Q, which is basically we have it per unit mass. So this is 1.2 BTU per pound mass, and we have basically 10 pound per second. So which means that we have 12 BTU per second. That's our Q dot. And m dot the same. We need to find H2. We have the exit velocity to be 900 feet per second, right? What you need to do here is also a conversion factor. So you can use basically the conversion factor from BTU to whatever unit that you want to convert every single information that you have from here, right? So your H is basically in BTU per pound mass, which is okay, right? This is gonna be BTU, so all the units gonna be the same, right? Okay, so now if you put the information in, you can find H2. So H2 is 1354.4 BTU per pound mass. This is basically per unit mass. And then we have the information at the exit. So P2 is equal to 200 psi, right? And then H2 is also equal to 1354.4 BTU per pound mass from the first law of thermodynamics. Again, use table A6E and find the temperature. So temperature at the exit is going to be 662 degree Fahrenheit, and that's basically the second part of this problem. So please let me know if you have any questions. One thing probably you would need is the conversion factor for the velocities. So your velocities is going to be feet squared. Velocity square is feet square per second square, and the conversion factor for this to be in BTU per pound mass is 25,030. This is 37. So 25,037 feet squared per second square is 1 BTU per pound mass. So this is the only conversion factor you would need here, right? Because all the energies are in BTU. So this one would help you to convert velocities to BTU per pound mass. So please let me know if you have any questions.